And so, the jargon I'm going to talk about something called post-quantum cryptography, and I'll not exactly explain, but sort of say what that is and how we got there and how this relates to other events that have occurred. And if you want to go to sleep, the short story is this is the fourth big transition in cryptography that we've had in a century. And so I assume there's going to be a fifth, but we have no idea what it is. Now you can go to sleep. Okay. So the main theme, as big a theme as any in the current world, is that we're going digital, or that we're going into the internet, that we're putting as much of human culture as we can into digital formats. Now, people are quick to point out, of course, it won't all fit, right? I mean, internet may be good for your sex life, but it isn't so good for getting some sleep afterwards. I mean, all sorts of things you can't do in the internet at the moment. But I think it should be regarded in some ways, think of Rome and Venice as city-states that were the capitals of empires. Right? So in some sense, not very much of it fits in the internet, but what does fit there is tremendously important and tremendously influential for everything around it. And so we are taking major elements of our society, and I've got a short list of them there, but certainly includes what seemed unlikely, I think, to most people, personal relations. When my late wife was interviewed by the RSA conference a few years ago, she said she remembered in 1973, we were sitting in a park running the dogs, and I was explaining to her that we were moving into a world in which people would have intimate relations with individuals they had never met. And she said, well, I didn't believe him, but I ran off with him anyway. That seems to have come to, I now know many people who are in exactly that position. So in particular, we're probably going to look most today at the impact of economy on these things. Okay. So naturally, what do? We try to copy as much as possible of what we did, just translate it into internet terms. And sometimes that works and sometimes it doesn't. A fair amount of it does. But one nice thing about this is occasionally I think we hit very pleasant phenomena. Two of them I can think of, minor ones, I think, but well, hypertext is just wonderful. If what existed in this abstruse form of looking at the end of the book for the references, and then even if you're sitting in a fine library, you have to go walking off and look at a catalog, you go dig the reference up. Now you just go click, 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 and you can find those things. Another one is an interesting, I would never have expected this, impact when you've written a book and you do radio interviews about it. Now that has a very direct, measurable influence on your sales. That is, people listening to the interview go straight to Amazon and buy a copy for their whatever it is, telephones or something. So you get some cases in which it's very hard to do something on the internet, other cases in which, it turns out to have all sorts of new and delightful properties. So what I'm going to come in on, largely not exclusively, is internet commerce. And this is, think about implementing this. Lots of things we're doing, look at back, it has to do with how do we connect what we're doing now with the infrastructure we have built already. Right? So in the case of internet commerce, it's largely connecting credit cards to transactions on the internet. But it's a matter of something that's a main theme in computer science, which is relating different namespaces. So you have a space of, names of people, names of companies, locations, email addresses, product numbers, things of this kind, and you're trying to keep these all smoothly and correctly related. In an environment, of course, it's in everybody's interest to cheat. And so the security aspect of this is organizing these things to make cheating as difficult as possible. Okay. So now I'm very fortunate. I get, I think, more credit than I deserve for security on the internet and less blame for insecurity. I recommend that if you can arrange it. Security is an awful state, and cryptography is no longer, I think, I mean, if you said to me, here, I want to do work that affects the security of the internet, should I work on cryptography? And I think the answer is probably no. You should work on how we can write better code, how we can get updates, guarantee updates, how we can avoid the problem that when an update goes out, the opponents begin studying it, and they have several months before everybody gets the update installed, but they've seen what vulnerability it repaired, and they go after the people who haven't installed it yet. Right, a million of these problems. But the best cooked part of this, and a very attractive field that intellectually, which therefore continues to draw lots of people, is cryptography. And at present, we're in a situation where there's a very plausible claim that some, by no means all, but some of the cryptography we're using is being threatened by new develops in physics and computer development and so forth. Okay. So that situation, and I'm going to say some things here that get explained later. Something called quantum computing is the beneficiary of a lot of optimism. It's been around, people have been talking about it since 1990. Sarcasts say, oh, well, you know, it's always 30 years away or something like that. And how accurately that captures the situation, I don't know. But the basic notion is this, that you have a bunch of molecules or something, and they're doing a computation. And they don't have to do just one instance of the computation. They can do it all of its possible things at the same time. This is called superposition. It's one of the great divine mysteries of the quantum mechanical church. And so, loosely speaking, this looks very much like something you're also probably familiar with, which is polynomial complexity theory, the P equal NP problem, things like that, where you have a circumstance where you look at a set of problems where if you could guess the right answer, then you could verify it very quickly. And those are, for abstruse reasons, called NP problems. And nobody knows whether that's really any better than what are called P problems, things that take polynomial time, whether if you can solve one, you can solve the other or not. And superficially, quantum computing looks a bit like that. However, it's really what it is not, so to speak, unboundedly parallel computing. It's sort of Avogadro's number in parallel computing, but functions in a pretty similar way, that something in effect goes and cooks up the right answer very, very quickly. And it only works for certain problems. It's not a sort of a general mechanism of computing, but potentially some of the problems we believe it works for are going to be immensely useful. So if you think issues of protein folding and scheduling and things that are computationally very difficult, maybe we'll be able to do them much, much faster with quantum computing. But in particular, one of the things it'll do, and I will show you in a little detail how it does this later, is that it may break cryptographic mechanisms we developed in the 70s that came into their own in the 90s, that are now used to protect the internet. And it's a business, this is a wonderful circumstance, right? We have this potential threat. Nobody knows how quickly it's coming along, 10 years, 20 years, 30 years. I can find you experts who will testify to each of those periods of time. But wait a moment. There's a business opportunity and an engineering opportunity that have been created by the National Security Agency and the National Institute of Standards and Technology because they've decided there is a threat and they produce new standards that people are required to meet, probably in particular to do business with the federal government. And so there's a business opportunity to sell a new kind of crypto system to people and engineering opportunity to develop the implementations of the systems and the protocols that go with them. Okay. So I'm going to look at this in two ways. One, I'll say a little more about each of those things. But I'm also going to say, well, wait a moment. Where does this fit into the context of what's happened to us in the past, cryptography in particular, in the past roughly 100 years? Okay, so I've been saying cryptography over and over again, and it's possible that everybody here knows better what it means than I do, but I'll give a definition anyway, which is a matter of transforming data. You know, you start out with something that's in plain text English or Chinese or American Sign, and you transform it into some kind of garbled, jumbled garbage that nobody can understand except people who know particular secrets. And that paradigm goes back thousands of years, but it has been developed a great deal in the last century. So I'm going to give you sort of what I call the managerial view of cryptography. It says nothing about how to do it, says what it gives you. And the key point, you imagine you're trying to protect messages. That's the keep messages confidential. That's the great classic cryptographic problem. And you have a building or possibly even a campus, right? And you don't want anything to leak out of it. I mean, I was at a ceremony at NSA yesterday. Perfect example of such a place. A number of buildings on a number of acres inside a big steel fence, and they're fairly successful in keeping a lot of things secret. Well, how would you secure communications within that campus? Well, in fact, what they do for most of it is they have a separate set of phone circuits, and they guard those fairly carefully, and they communicate on those. On the other hand, if you had an office in Hong Kong, or an office on the moon, or just a satellite in space, or ships moving around, now you have a problem, right? Because, you know, you can't run cables, all of them, let alone guard the cables. And so you need something that protects things independent of the path along which they travel. And cryptography is the thing that does that, by and large, better. Not quite the only thing that can be used in some circumstances, but it is very flexible and can be very secure. In particular, it allows you to pass the message directly through the hands of the opponent. So imagine you can be carrying, in effect, a letter of introduction to me, and you can't read it, but that doesn't, and you can't tamper with it. If you change it, if you're carrying it, perhaps you have an ability to change it, but if you're changing it, it'll change in such a way that I'll recognize that and I won't accept it. So this gives you a very, very powerful tool for moving information around in environments that you don't control, and nonetheless being confident that the information will not be changed, will neither be understood by people you don't want it to understand it, or changed by people you don't feel authorized to change it. The other point is cryptography acts like an amplifier. So you imagine you have a small secret, by which I mean, 128 and 256 bits are common amounts, but it can be larger than that. A few thousand bits still isn't a lot of information. And you do something that leads the security to maybe terabytes to be equivalent to the security of the small number of bits. And exactly the case you imagine. There's a satellite communications link. There's one of these small keys in the radio at one end and at the other end, and you transmit gigabytes of information. And as long as you keep those keys secret, then the gigabytes of information will not be readable by anybody. And if those keys are compromised, suddenly the gigabytes of information become available to people. And so the virtue of having something operates as an amplifier is that now you can take the small pieces, which fit on your disk or in your fast memory or something, and you can shuffle those around. And so one description has been said, the purpose of network security is to turn security problems into key management problems. Now, in the 1970s, and I'll get back to this in other contexts, we developed a new sort of system that has different properties from the crypto systems that have been around for hundreds of years. We're able to separate the ability to encrypt messages from the ability to decrypt messages. It's one way of looking at it. And so I can know a key that is in the public phone directory, that's your quote public key, and I can crypt a message that way, and you have a corresponding secret key that you can use to decrypt it. I mean, note that has great, ignore details, but one is functionally what happens. I want to send a message to you. I get the phone book. I look up your public key, and I encrypt the message with it. I don't have to worry about waiting to get a certified letter from you or any of the things that were done, have been done, still being done in cryptography to manage keys. The other way this can be used, and a key way that it is used, is what I call now, we misnamed it originally, but it's really called key negotiation. So I want to talk with one of you out there, and I send you a message, and you send me a message, and I send you a message. And at the end of this negotiation, even though everyone else has their ears cocked and gets every single bit of it, we know a secret that nobody else in the room knows. And so that's as though you had perfect bridge bidding, right? I mean, if you're South and you're playing with North against East and West, the bidding process in contract bridge is one in which, in effect, you're talking to your partner a little better than you're talking to the opponents, and you end up knowing more than they do. It actually, doing it cryptographically is forbidden by the rules of bridge, but if you were able to do that, you'd come up with knowing with a perfect understanding. Oh, someone of the NSA people wrote a paper you can find called Cryptographic Techniques in Bridge Bidding. There are a whole big lot of bridge players at NSA. The last point is there's another thing, this is all about looking at symmetry versus asymmetry. And there's another asymmetry that's very valuable, which is I'm able to sign a document, and you're able to recognize the signed document, but you couldn't have produced it. And so, if you note, in human signatures, we depend very heavily on the fact that they're hard to reproduce. And in digital signatures, of course, a digital document can always be copied perfectly. But the difference is, but you can make the digital signature depend on every bit of the document. And so you can copy the document perfectly, but then you just have another copy of the same document. And if you change it, you can't necessarily create the signature for the new document. So it's those things that in many ways have made it possible to scale cryptography to the dimensions of the internet. And it's those things, the current techniques for doing those things, that are under threat. Okay, there's just a listing of some systems. Amazingly, interesting things last a long time. The one that impresses me is Bitcoin, that the original system that came out in 2009 or so is still running around making people lots of money. Similarly, we did all this work circa, 1975, 1980, and basically these things with this modification are still very much in business. In essence, what's called elliptic curve cryptography uses fancier arithmetic than we used at first, which means you can use smaller numbers. So the numbers come down from a few thousand bits to a few hundred bits. That was developed by two interesting people who were remarkably different. Victor Miller was working at IBM, and then for a long time, he worked for the NSA consultancy in Princeton. Neil Koblitz is a communist, and he's a mathematician at the University of Seattle, and has been working for a long time with Vietnamese. They share the credit for one of the greatest discoveries of the late 20th century in cryptography. Okay. Now, come up to 2005, in a reasonable sense, you could have thought we had outright solved the problem. Something I predicted in 1980 in the paper I wrote was that military government crypto systems and commercial ones would converge sometime around 2000. And I got that prediction right. So in 2005, NSA published something called Suite B. It had presumably Suite A with some bunch of secret algorithms that used for the same thing. But Suite B consisted entirely of public crypto systems. They were most of them federal standards, and they declared that they would use them for everything up through top secret information. And then subsequently, they did begin to do that. And the four essential pieces, there's something I won't say much about today. It is the strong symmetric crypto system, classic crypto system. It's called the Advanced Encryption Standard. And it was developed in a big international contest between 1997 and 2001 or so. Secure hash algorithm 256 and 384 are NSA designs, and the object is to be able to produce something that's in effect a label. I like the term message digest or something that's inseparable from a large object. You can't find any two of them with the same hash. Something called elliptic curve Diffie-Hellman and elliptic curve digital signature algorithm. So it appeared at that point, well, maybe, you could have looked at this as well as we know that any cryptographic system is secure. Those look secure. Why should we work on this problem anymore? Maybe we should go do something else. Then people began to suggest that quantum computing was going to be able to break these things. And in particular, in the late 90s, a mathematician named Peter Shor developed an algorithm I'll be discussing in a little bit. But quantum computing is, as I was saying, superbly parallel. It's been promised for 30 years, for a long time, and I guess I'm willing to believe that promise. And if it comes through, it will break the current systems. Okay. Okay, now how does it do that? Well, note that public key cryptography differs fundamentally from symmetric cryptography. If you're a cryptanalyst, you're attacking traffic in a symmetric crypto system. And let's assume that you know what the system is. You've already done what's called diagnosis, figuring out what system is in use. And nonetheless, you can do statistics on the traffic and a variety of things like that. But you cannot, until you know the key, you can't encrypt or decrypt anything. So there's certain kinds of experiments you can't do. On the other hand, in public key encryption, you know the public key. So if you have a message, well, you don't know the secret key, you can't decrypt it, but you can encrypt it again and again and again and again. Right? And doing that gives you a great advantage because you can go forward, and you may be able to go forward a very long distance. It's going back that's hard. Okay. So if you look at RSA, and I'm sorry, I'm not going to take time to, I expect most of you know how it works, but the key point is the public thing is some large bicomposite number, has two prime factors. The secret thing viewed one way is those prime numbers. Viewed another way, it's what you do with the prime numbers, which is produce a number called phi that's a cycle that everything is on in the ring arithmetic associated with this. So looking, there's a cycle, P and Q are the factors, there's a cycle of length P minus 1 times Q minus 1, and knowing that's equivalent, and the number is equivalent to knowing the factors. So you can regard this as, what do we want to do? We want to find the length of a cycle. And if we can do that, then we can go all the way around the cycle and stop just before where we started, and that would be the answer. Now, it's like being on a racetrack, right? Now, you can only move one way around. You get 3 points if you know what racetrack that is. Okay. You can't go back on a racetrack. I mean, think about it, you're going to get run over. But you can go forward. And if you can go forward far enough, fast enough, you can get to any point on the track. What is critical to do that is knowing how long the track is. So in RSA and Diffie-Hellman, the secret thing is some cycle length. But if you can find the cycle length, then immediately all the secrecy goes away. You can do anything that you want to. So it's like, imagine, you don't know what latitude you're at. So you move all the way around the Earth, but you don't know where you're going to get to unless you know how far it is around the Earth at that point. Best simple example I can come up with. So in 1996, I think, Peter Shor developed what's called Shor's algorithm. And Shor's algorithm finds cycles in finite structures. If you think about finite mathematics, right, you have some set of things, and you have some way of changing them. Well, on an infinite set like the integers, right, 0, every time you add 1, you get a new thing. 0, 1, 2, 3. You never find any place where adding 1 to something brings you back to something smaller. Always gets larger. But if you had a finite number of things, like the dozen things on a clock, add 1. After a while, it's 11. You add 1, you get back to 0. And that's going to be true no matter how large the set is. Any transformation is going to take you along a cycle. And the key point, if you can go along the cycle fast enough, then and if you know the length of the cycle, then you can get anywhere. Now, it happens to be a property of exponentiation, which is what we use in these systems, that you can do it very fast. So loosely speaking, if you can go around that track in once in 1 microsecond, then you can go around it 1 billion times in 30 microseconds. So you're going to be able to get anywhere if you know where you're going. Okay, so that's the reason Shor's algorithm finds cycle lengths and breaks the current systems. Now, the problem with that is Shor's algorithm requires what's called several thousand, quote, good quantum bits, qubits. That is to say, they aren't noisy, they stay stable, etc. And these are all big engineering problems in the development of quantum computing. And depending on who you talk to, it's either only a few years till we solve them, or they'll never be solved. You bet your career on this one. So what position does this put us in? Let's look at a broader issue. What's the lifespan of a cryptographic system? Right? Well, it takes a few years to design. The design of the advanced encryption standard, in some sense, started in 1997. It actually draws on work done in the mid-90s, earlier than that. The system was declared standard November 26, 2001. That's total 5 to 10 years to build the system. Others have taken more and less time. Then how long it took? Actually, probably took 20 years to get it widely installed. By 2020, I believe it was the most used crypto system by far on the internet. How long does the equipment last? Well, equipment, there's some US military equipment that certainly same pieces of equipment went into service in the 50s and retired in the 80s. A piece of equipment could be around 20, 30 years. Some things are only around a few years. But the crypto standards used in them could easily be around for many decades. There's a US system that was introduced in 1968 that's I still believe, still in equipment that's being used. The data encryption standard, the ancestor to the advanced encryption standard, is still in use by the banks in form of what's called triple DES, and probably will be for decades. So it's one of the facts of cryptography is things don't much go away. And then the final issue is, what's the life of traffic? Well, it depends on what it is. But if you look at US secrets, basically the basic rule is something that's top secret leaks down to unclassified in 30 years. There are lots of exceptions to that, but so you sort of think, that's not, there are census things that are kept secret for 50 years. You can easily imagine details of how H-bombs work were discovered in the 50s, and lots of those are still secret. So lots of secrets. You can easily imagine a secret many decades old. So what is the lifetime you need for a cryptographic system? It's decades, maybe 100 years, maybe longer. So what are we going to do under these circumstances? Face a new threat, a need to change crypto systems, and what is it? Well, this began as an active project, so to speak, 9 years ago with, I think you should read that. I want to read. That is the most deliciously indiscreet memo I can ever remember seeing. If you haven't spent your money doing what we've been browbeating you for 5 or 10 years to do, well, maybe you should save your money because we're going to browbeat you to do something else. And that line, there will be a move in the not distant future. Well, not distant has turned out to be 9 years. Okay, that's sooner than it could have been. This became a lot solider 2 years ago. And NIST, acting in part for NSA, jointly with NSA, proposed a number of new cryptographic algorithms for evaluation. And they quote, the jargon is, they went out for comment. They'd already been studied for a number of years, been a number of workshops examining them. And that crystallized about 2 months ago in 13th of August, 3 new cryptographic standards with pleasantly colorful names were adopted. And these replace the things I showed you, or can, in principle, will replace the things I showed you on other slides, like Diffie-Hellman and El-Gamal signatures. There is now a substantial ongoing several years of work to get these things implemented, because they have some different cost characteristics and generally different characteristics. I see somebody taking a picture. Incidentally, I'm assuming the department will be, I'm happy to have the slides put up on your website, and I'm assuming you're able to do that. So I was, one of the great things, discoveries of my youth, we got to where we suddenly, classic mathematics teaching was just dreadful. Professor sat there and wrote the theorem on the board, and people copied it and so forth. And to me, it was just an overwhelming discovery. First had transparencies. I could hand out what I was going to show so people could take notes right on that. You don't have to write down something that's already been written. Ah, well. Okay. So I want to mention, since one very important cryptographer said at the RSA conference this year or last year, are these new, quote, lattice-based systems safe? And there was a paper from Beijing purporting to show how to break one of these things. And intensive work by the referees found a bug that I remember as being at the bottom of page 37 out of 64, and it was found in like 2 or 3 weeks. And Adi Shamir's response to this, Adi, who studied this, I haven't, said, yeah, this one had a bug in it, but the amount of interest that was stirred up in it may in fact lead to new work in this area. And so, you know, take that for what it's worth, or take it that I don't know what it's worth. Okay, so NSA, there are two kinds of standardization going on here. NIST produces what are called Federal Information Processing Standards. Produces other things, but that's the ones that concern us. And those are basically binding on the federal government and derivatively on anyone who wants to do business with the federal government, and derivatively of that on U.S. industry in general, and derivatively again because of U.S. influence on worldwide activities. NSA sets a set of standards that are more rigidly enforced, that are about people who are processing what's called national security information, which includes all the stuff that they call secret, but it also includes some other things. And you might think about satellite control data or things of this sort, things that affect, in their view, the national security. So they publish the standards for that. And as it happens, loosely speaking, the NIST and NSA standards are currently in harmony. There's a lot about this that people think is new that isn't. The jargon currently is harvest now, decrypt later. The proper intelligence terms, or the classic intelligence terms, are collect now. As the taxonomy says, you have access to communication, you collect the communications, and then several levels of how you process communications. And you exploit it later. Now, that later could be quite a while. In one of the biggest cryptanalytic projects ever to become public, it's called Venona. There was a serious Russian mistake made in 1942, which led to, and I'm sorry, I'm not going to go into this, the jargon is reuse of one-time material. There should only have been one occurrence of it. There were two. They were, in fact, all over the world in different communication systems, very hard to find. People went on working on that problem. It was finally closed in 1980. It led to the death of the Rosenbergs. The big thing, it was believed to contain secret messages that might tell you that people who were very high up in the security services by the 1970s had been communists in their youth in the 1930s. But that is lots of things in cryptography go on for a long time. But this has been happening at least since World War I. I guarantee you there's traffic people are still hoping to read from World War II, and very possibly from as early as World War I. Probably not much earlier than that, because I'll come to signals intelligence is really a derivative of radio. Okay, so I want to look now at the historical context of what we're in. And roughly, I'm going to tell you, about every 25 years, we've had a big upset in cryptography. And there are always two aspects of it. I find two aspects of it. There's some new challenge, something you can't cope with the current stuff, and there's something new that makes it possible for you to cope with that challenge. If there's not any new challenge, nothing changes. And so far, there hasn't been a new challenge that we haven't had a way of coping with. But one can imagine that. So what I call modern cryptography goes back quite a long way. Right? It was, as I put it, was conceived, has one odd creature. It has one birth, but it has two conceptions. It either dates from about 1,200 years ago in Baghdad or from about 500 years ago in Rome and Venice. And why do I call it modern? Well, those people understood why what are called monoalphabetic crypto systems, which were being used at that time, weren't any good, what you had to do about it, and developed what are called polyalphabetic crypto systems that basically involve two things very familiar to you. They use table lookups and they use some kind of arithmetic, largely modular arithmetic, modulo 26, but certainly very possible to use other things like mod 2 or Galois arithmetic, etc. So the basic elements of cryptography all the way up to the 1970s have been known for hundreds of years. Now, why didn't that lead anywhere? It's not that nothing was ever done with it, but basically, without machines, you can't do the computation necessary to do these crypto systems well enough to be worthwhile. And in particular, if you think of yourself as a code clerk working under battle conditions or something like that, doing a complex computation by hand is very dubious. Once you have machines to do it, you do a lot more computing very readily. So I've mentioned those are the basic notions. You have just two things, and exactly how they work varies from time to time. And if you look at the advanced encryption standard, you see a perfect example. You have an 8-bit table, and you have Galois arithmetic with a particular Galois field that's used. Okay. Sometimes I get ahead of my slides. Okay. So in essence, modern cryptography was born in World War I. The challenge was radio. You think internet is wonderful. Radio was just fantastic. Nobody ever had any way of communicating with something moving like a ship before radio, or barely. If it's in sight, you can wave flags at it or flash lights or something. But talking to an over-the-horizon ship was impossible before radio. And the first Sea Lord, Britain, commanded the greatest fleet in the world and didn't know where it was. They had a snooker table. They had model ships on the snooker table. They get word, oh, this one put out of port in India 5 days ago, because they had faster land communications. They had telegraph and stuff already. And within a few years of the introduction of radio, it became like making any other phone call. A few years, up to a small number of decades. It took a while, but now you can reach any ship except for some submarines immediately. Right? And so that gave the first Sea Lord and other commanders control of these forces they had, changed their fighting effectiveness completely. Now, that was the challenge. What it turned out there was in response was that we had electricity since late in the 19th century. And over a comparable period, we began to have good machining. You could make mass-produced parts that would do computation, that mechanical calculators and such have the same technology that could be applied to cryptography. And the thing that became very popular is obviously called a rotor. That's a lookup table. It's wrapped around in a circle so that you can do the indexing by rotating it. And that particular thing is an Enigma rotor. For no reason I can quite understand, Enigma is the best known maybe crypto system of all time, but of World War II. And in effect, it is a sequence of table lookups. You have 3 tables, you have their indexes, you look something up, then you change the indexes, and you look the next thing up. That is the essence of polyalphabetic cryptography. It keeps changing the alphabet in which you encrypt something from character to character. That is the fanciest of the World War II crypto systems. It was designed by an American named Frank Rowlett, and it is the enigma that I was showing you before, it just has a simple odometer counter. The first wheel turns and it turns and it turns. After a while, it ticks the second wheel and the second wheel turns. This one is two rotor machines in one box. And the first rotor machine manufactures the rotations of the second rotor machine. So I just telling you this to give you some indication. The response to the challenge and opportunity of World War I took perhaps 20 years. That's a 1935 design. So World War II was fought using the things inspired by the events of World War I. There's another sort that's interesting. I won't say anything. They're called pinwheel machines, designed by a brilliant mechanical engineer, cryptographer named Hagelin. That's a thing called the M209 that was widely used U.S. Army. I want to talk about two more things, maybe just for the fun of it. One of the greatest cryptographic insights of early 20th century is Japanese. And much to the good luck of the Western Alliance, they took a brilliant idea and produced lousy crypto systems out of it. The idea is, the most important aspect of the idea is, why should we use rotors? Rotors have all the charm of distributor caps. I know you people are too young to have driven cars from before digital ignition, but distributor caps are low voltage things that develop carbon arcing across between terminals, and rotors do the same thing. Rotors interest nobody but cryptographers. That means they have to be developed out of the smaller cryptographic budget rather than the larger communications budget. What the Japanese did was use stepping switches. And stepping switches are what telephone networks were built out of at that time. So if you think of an ordinary telephone central office, it might have 100,000 of those things. You know, they're highly reliable. You go to Nippon Telegraph and Telephone and buy one. You don't have to design it. And just incidentally, it's a better cryptographic component. A rotor is a single lookup table. I won't go into the details, but a stepping switch is what's called a Vigenère table. It involves a whole bunch of independent lookup tables and index that carries you from one to the next. All of this brought us up to World War II, and now we have two new, less spectacular but important challenges. The first one is volume of traffic. Entering World War II, all right, with that SIG-ABA, we had in US forces had very secure teletype communication at 10 characters a second. What are you supposed to do about voice, which is at least, a dozen times that fast? Let alone, we would ultimately want satellite cameras, TV conferences, etc. The other thing that was a big secret then was computing. Basically specialized compute. One of the roots of computer engineering is specialized computers built during World War II to attack cryptographic systems. Particularly a system called Colossus, designed by a man named Tommy Flowers for Bletchley Park in Britain. They attacked a system called the SZ40, which is the high-grade German system, higher grade than Enigma. Now, I mentioned voice. That is the world's first digital telephone. Filled a room not quite as large as this, had 32-meter tall telephone racks of equipment, cost, I don't know, millions of dollars. It was so expensive that initially only Roosevelt and Churchill could afford one. By the end of the 40s, there were actually about a dozen. The US four-star generals all hopped up and down, and they wanted one too. But the point is, that thing is interestingly like modern secure telephones. And it's unlike it in a lot of ways, but it runs 2,400 bit per second voice. Well, something the great breakthrough in secure telephony was in the 80s, was something called STU-3, the third generation secure phone, and its basic operating rate was 2,400 bits a second. So this, of course, has now come down to where it fits in your pocket and operates at much higher speeds. And by comparison with the digitizing the voice, the cryptography was a small part of this thing. Okay. This revolution is not so readily pinpointed, but involves several big things. It started out with custom electronics. They evolve over time to look more and more computer-like. Roughly speaking, they run from a bus width of 1 to 4 to 8. And so they look very much, in the end, like an 8-bit computer. And there's another start that begins at this time, that what's popular with us today are what are called block ciphers. Take 128 bits, produce another 128 bits, and you use that as the basis for everything. World War II and on, quite a number of years, the basic thing was sequence generators. And the relationships between the two were not yet as well understood as they are now. The third big event is late 20th century. It's a vast change of scale. I mean, you know, the world's banking network has thousands or tens of thousands of points on it. And they used to have a scheme, I don't know if they still do, you used to be able to go into a bank with a certified check, and they'd pull out this big book, and they'd look up the signature of the bank president who'd signed your check. Well, similarly, cryptographically, you could do all of that, if you had to, with conventional computing and with non-public key cryptography. And I would actually, you know, advise that in lots of cases. But the internet was a whole nother thing, right? We don't have, when the military bought cryptographic equipment, 100,000 was a big order, right? The contractors were jumping up and down to get at it. There were the set of cryptographic systems that's in your telephone, that's in every browser, is better than any of these things showing you pictures of. And there are billions of them in the world. So we're operating on a whole new scale. And the importance of public key cryptography is it allowed you to have secure communications with people with whom you had very little contact. You not only hadn't gotten letters from them ahead of time, you might just have contact with them once. And you don't want delay. You want to log in, you want to buy something. Maybe it's going to be delivered online, like it's a book, and you get it on your phone. So basically, things went on from the special purpose electronic machines that grew out of World War II to a variety of much more flexible things like software. And the key thing that happened as a result was too many people in the world had to use cryptography. The governments could no longer keep it secret. Public key played a big role in this, incidentally, because it's a cryptographic problem for which you can't just sit down and write down a solution that looks like it's good and put a lot more work on somebody to say, no, this is no good, I can show you how to break it. Even getting one that looks as though it might satisfy the requirements is difficult. You don't have a clock, and I have no idea what time it is. If you need to go. If they throw me off the stage, they throw me off the stage. I'm operating in a vacuum. I only have about 2 more slides, so that's good. I have 5 minutes, okay. So this is the fourth of these events. Quantum computing has upset cryptography in the early 21st century. But it's not as though we haven't had this happen before. And it's different, of course. But the difference is largely positive. One, there are lots more cryptographers, lots more communications in cryptography. The public field is now huge. And in technical capability, I believe, is, yes, there are lots of things the secret people don't know that we don't know, because they work on problems that we don't work on. You can't do signals intelligence publicly, right? If you rub people's noses in it every time you're reading their traffic, they're going to do something about it. It would be rather frustrating. But the general fund of mathematical and computer science expertise is huge. And so the new technique here is that we have new mathematical problems, in particular, something called the lattice basis reduction problem, and we have new crypto systems based on that. Now, there's some competing challenges with this. So I'll bring to your attention. There's something called Internet of Things, smart refrigerators, but what's more interesting, maybe smart pacemakers, things living in environments where they can't be serviced, you can't change the batteries, they don't have very much power, maybe it's sensors sprinkled all over an enemy's territory. You can't get at them and service them. And so those things have to, if they're going to do encryption, they have very little power. And in the words of my friend Hillary Orman, who's a secure network designer, says, well, there isn't enough power to do encryption. Anyway, if they could find enough power, they'd do something else with it. So the competition between popular features and security. There's another wonderful development, and how it relates to quantum computing is as yet unclear. But there's this great thing that you have a big computer that I can't afford. And I have a problem I want it to solve, but I don't want you to know what it is. So I encrypt my problem and I send it to you. And you can't read it, but you can't execute it. So you execute my problem and it solves it. And you send me the bill and I pay you and you send me back the solution. And I can understand the solution, although it couldn't have done the computation. Amazingly, that can actually be made to work. And it was used, one of the problems it solved is called the problem of a black conference bridge. You have a bunch of secure telephones all talking to each other, and there's something that's moving the calls around, making the connections, and it can't understand what they're talking about. And it's not yet clear. This could, in some sense, think about it, this could solve all of your security problem, right? Because you don't have to, in order to use cloud computing, you don't need to reveal anything. You just send this encrypted thing you want computed on to the cloud, and the cloud, in its wonderful ignorance, computes on your problem and sends it back to you. So if you get that to be efficient enough and flexible enough, it would change the world. But it's not at all clear that you can. So basically, I'm talking there about the next few years, but what about 2040, 2050, 2070? We don't know, but I'm pretty confident from the fact that we have had a significant upheaval in cryptography every 25 years since World War I, that we should deal with the current one in the understanding that it is just the current one. There will be another one. Thank you all.